Okay, so what we're looking at today is going over what the Desmos intro activity went through, and you're going to have some formal notes on it to look so that you have these to look back on. You do not need to turn in the worksheet part of the Desmos activity. Okay, that y'all are just going to keep that with your notes. Okay. All right. So we've looked at graphs in the XY plane, the rectangular coordinate plane, with single equations with two variables, X and Y. And now parametrics introduces the third variable, okay, which we're going to refer, that's the parameter. Okay, so you can see here is a graph of time and vertical distance. It's vertical distance in terms of time. Okay, then this is horizontal distance in terms of time. So those are both rectangular equations. Okay, those are not parametric. You can, so like if a ball is thrown, we can see it starts vertically at 40 meters high. Okay, and so it must be tossed up. Okay, and then it gets to a maximum height, and then it falls back to the ground. And that takes about 4 seconds. Okay, horizontally, that ball was 0 meters away, and at the end of that 4 seconds, it was 160 meters away. But that's just a linear function for horizontal distance. When we introduce parametrics, we can look at the horizontal and vertical distance at the same time in terms of time, using time as the parameter. So we can see at 0 seconds, it started 0 meters away horizontally, 40 meters high. And then after 4 seconds, approximately, well, this one doesn't show it completely, but you get to the 100, it doesn't quite show the 4 seconds, but you can see where it stops here short of 4 seconds, because that's where the vertical distance would go negative. Okay, so it stops there. Does that make sense? So you're able to combine and look at two variables at the same time in terms of whatever the parameter is. Oftentimes it's time, it's not always time. All right, so this was mentioned in the Desmos. Oh, hang on. Some of this is filled in. Rid of some of that. We can do it together. Well, now you get a sneak peek of what that's going to look like, but that's all right. All right, so in the activity, it said we're going to write x as a function of time, or a function of t, and y as a function of t, but it's two different functions. So we have an x equation and a y equation using that third variable t. So in this first example, we want to graph this curve of this parametric equation. So the parameter is going to have a given interval. The parameter is going to be limited. Okay, so over the given interval, that's telling you your parameter. Okay, so we're only going to graph this from where t is -3 to +3. Okay, they've given us the x value, or the x equation, and the y equation. So we need to come up with a table of values for that from when t is -3 to +3. So the easiest way for you to do that is in your graphing calculator. This was toward the end of the Desmos activity. There was the slide, I think it was green, that explained the calculator settings. If you need to go grab a calculator, you don't have your own, go grab one real quick while mine's loading. All right. So the first thing we're going to check is that we go to the mode button here next to second. So we go to mode and we make sure on the fourth line down, we're in parametric mode. So you're going to scroll down and over and hit enter to make sure if parametric is not highlighted, if your calculator's still in function or if it was left in polar. Okay, so you're going to select parametric mode. Once you've selected that, when you go to the Y equals button, it's not going to be Y1, Y2, Y3, etc. You've got your pairs of X and Y equations. So our first parametric equation is going to have an X equals and a Y equals. So on our paper, that was the X was T squared plus 5. So to get T, it's just your variable button, the same button we usually hit to get X. Excuse me. But when you're in parametric mode and you hit that button, you get a T. So T squared plus 5. And then the Y equation was T over 2 plus 4. Remember, to get a fraction in your graphing calculator, to get an actual numerator over denominator, you can hit alpha Y equals, and you get that N over D, numerator over denominator. And so then you just hit enter. So alpha Y equals enter gives you this fraction setup. And mine is T over 2. And then plus 4. Now, if you only want to look at the portion of your graph, bless you, for your given interval, go to window, just window. And you're going to set up your T minimum and maximum. I just need to see -3 to +3. Okay, that's all the graph that I need to see. Okay, now if you go to the graph, mine's cut off because this only goes out to 5. So I need to change the window settings. If you're not sure what your window settings should be, go to your table, go to second graph. I'm going to go to second window to do my table set because I want to just have it count by ones. The change in the table just to be by ones instead of by a decimal. So if yours is going by decimal values, you can go to second window. That gives you your table setup, and you can change that to a 1. Okay, but your starting value has to be an integer to be able for it to actually accept that that's going to be by ones. So now I'm going to go back to my table. And so I can see when T is 3, my X goes all the way out to 14. I go to -3. Okay, so 14 is the furthest right it needs to go. And then if you look at the Y values, 5 halves, 7 halves, 9 halves, 5, 11 halves. So the highest it needs to go is, all right, so I'm going to go back to my window and I'm going to change my X to be 0 to 15. And my Y's to be 0 to 6. So now I can see that whole graph. Are you with me on that? Okay, so this is what our graph should look like. Okay, we're going to plot that. To see the actual points, I'm going to use that table. Okay, so we said we're going from where T is -3 to +3. Okay, so I'm going to plot that first point when T is -3 at 14 and then 5 halves, which is just 2.5. So my first point, I'm going to go out there to 14, and this grid goes to 14. This last line is 14. 2.5. Okay, and then the next point was when t is -2, the ordered pair is at 9, 3. Okay, and label your x and y. And then the next point, when t is -1, is at 6, 7 halves. Okay, so that's 3.5, 6, 3.5. And then when t is 0, it's a 5, 4. And then when t is 1, it's 6, 4.5. And when t is 2, it's 9, 5. And then when t is positive 3, 14, 11 halves, which is 5.5. So 14, 5.5. Two, 3, 5.5. So then I can sketch that curve. So this is a parabola opening to the side. You do not extend past these points and draw arrows like it continues, like when we draw quadratics, right? Because this specifically only goes from where t is -3 to +3. So when you're graphing, we actually need to put some labels on this graph, some arrows to indicate the direction. So we started at this point when t was -3, and this is the direction we went, right? This is the path. So I'm going to just draw some arrows showing that direction. And then I'm going to label some of my t values. So this is where t was -3, where we started. This is where t was +3, where we ended. And then all the points in between. You can label all of them if you want, or a few. This vertex was where t was 0. This was where t was -2. This is where t was +2, +1, and -1. So if you want to label all 7 of those that we plotted, you can, or just like 3 of them, that's okay too, as long as we can see that that's the direction. As t is increasing, that's the path that we're following. T is what is determining your domain, essentially. T affects both the domain and range, because T is telling us how much of this that we're graphing. Because if I were to change this to rectangular form and just get the parabola with no restrictions, it would be just drawn with arrows on the ends continuing forever off both of those. Okay, but it doesn't because T is limited here. So what is the domain of this graph? What was that? Yeah, that was at 5, and this was at 14. So the domain is 5 to 14, inclusive, right? What's the range of this graph? If you wanted to leave those as the fractions, you could have. That's okay too. If you wanted to do for the 5 halves to 11 halves, you could write it that way. You feel okay about the process of graphing this using parametric mode in the calculator and looking at your table? Okay. B, I'm not going to do B with you then. It's very similar, but I'm going to give you the scaling to give you like a little help to get you started. But then I want you to practice going through that process in the calculator. Okay, this is your parameter is limited to -8 to 8. Okay. So I scaled the x-axis by 2s. So 2, 4, 6, 8, 10, etc. I just labeled a couple of those. And then I scaled my y-axis by halves. Okay, so every 2 squares was 1. Okay, so that way when y'all do that, we'll all have the same graph because we'll all have scaled the same. Any questions about that process in the calculator? Okay, and then don't forget you have to draw those arrows on your curve to show the direction, the path, as t increases. All right, so then let's flip to the back and let me apparently erase what didn't get erased. Okay, so let's look at these together. So in the Desmos activity, you did, it took you through practicing eliminating the parameter by solving for t in one of your equations and then substituting that into the other equation, right? So you'll have had a little bit of practice with this. Okay, so I'm going to go through for number 2. They just want us to put this parametric set of equations into rectangular form or as a Cartesian equation. Okay, so which one of these would be easier to solve for t? I think the x, because over here t is squared and I'll have to end up with positive, negative, all that equation. So I think this x equation is going to be the easier one to solve for t. Okay, so if I want to solve for t, what am I going to do? Divide out the coefficient, -3, good. So I end up with t equals -x/3. Everybody okay with that? Or you could write it as -1/3 x. That would be the same thing. Now you're going to make a substitution. You're going to take that t value you just found and substitute it in for t here in the other equation. So far, so good? We just did this substitution here. All right, now we're going to simplify. When I square a negative, it's going to come out positive. When I square a fraction, I'm going to square the numerator and the denominator. So that's going to be x²/9. And then I've still got +2. Can be written this way, or if you prefer to write it with a coefficient of 1/9, and then your x² +2, that's the same thing, right? So either one of those is good. So this is your process for putting a parametric into rectangular form or writing it as a Cartesian equation. Solve for t and substitute that into the other equation. It's just like you did in algebra when you had systems of equations, right? Use substitution to eliminate one of the variables. All right. Let's look at example 3 here then. This one wants us to write this in rectangular form, and they also want us to graph it. Okay, so we're going to write the rectangular form, and we're going to look at the rectangular equation graphed, and we're going to compare it to the parametric equation graphed, because we're going to notice some things. Okay, so first, the changing it to rectangular form. I'm going to solve the x equals equation for t. What am I going to do to solve for t? Say that again. I could do that first, but it might be better to first try and just get it out of the denominator. So if I just multiply it over to the other side, it's no longer irrational with a radical in the denominator, and my t that I'm solving for is no longer in the denominator. So now I've got this. I still need to solve for t, so how do I get rid of that x? So divide the x over to the other side, which will reduce there. How do I get rid of a square root? So I square both sides. So again, square the numerator, square the denominator of 1 over x squared. So now that's my t. That's what I'm going to substitute in for t in the y equals equation. So I've got 1 over x squared plus 1 over 1 over x squared. Okay, so what can I do to simplify this? We don't like to have fractions within fractions, right? So what can I do? Yeah, flip and multiply, right? So instead of dividing by 1 over x squared, I could multiply by x squared. Be careful, this is a binomial, so the entire thing needs to be in parentheses multiplied by the x squared. So that x squared is going to get distributed. So what's x squared times 1 over x squared going to be? 1, and then that would just be plus x squared. Okay, so I get this equation, and if I were to graph this, this is just a quadratic equation shifted up 1, right? Okay, so don't draw this yet. Let's just visualize this. If I had a quadratic, do not draw this yet. It would look like this, right? That would be my quadratic. Okay, but I need to compare that to my parametric. Okay, so you've got a visual in your head of what the quadratic would look like. But when I go to y equals, and I put in my parametric equations, which were 1 over the square root of t and t plus 1 over t. Okay, I'm going to go to my table of value. Notice I'm getting errors here in my table for size. Why do you think that might be? So let's go back on x's. I'm getting several errors for all of these negatives. X, when t is negative, x is an error. And then I've got an error also at 0 for both the x and the y. So let's look at those equations again. T for the x equation is under the radical. That makes sense that it can't be negative, right? You can't take the square root of a negative. Okay, why can't it be 0? I can square root 0 because it's in the denominator. You can't divide by 0. So our x is never going to come out to be 0 or negative because it's 1 over a positive, right? So there's no way our x is ever going to be negative or 0. So that limits this quadratic to where x will only be positive. So if I'm going to graph it using the rectangular form, I have to understand that restriction. That restriction, our domain is determined by the t, right? By the parameter. So if our t cannot be 0 or negative in this specific equation, the x will never come out 0 or negative. Are y'all with me on that? And for the y, the reason that y had an error was because t is in the denominator. You can't have 0 in the denominator. Okay, so looking at the parametric table in the calculator helps us realize, oh, there's some restrictions there. So our t value has to be greater than 0. Okay, so notice though, as the t increases, what's happening to the x? It's decreasing, right? What's happening to the y? As t increases, what's happening to y? It's also decreasing. So x and y are both decreasing as t increases. So that's going to help us just show our arrows on our curve. Once we draw it, we'll know that the arrows, it's going to, as t increases, x and y are going to be coming closer and closer and closer to where they started to close. It's going to be coming like down that curve. Okay, so if you want to graph it using the rectangular equation, you can. We just know that we cannot, x is not going to be 0 and it's not going to be negative. So normally that vertex that's would be at 0, 1 for this would need to be an open circle. Okay, and then I could plot the others, over 1, up 1 from there, over 2, up 4 from there. Okay, and I could sketch that curve. Or I can use my parametric table. I know there's a point at 1, 2. Go over 1, up 2. Oh, that's the same point I got by graphing the rectangular. How about that? Now, here's where the issue comes for as t gets higher, these are getting to be smaller and decimal fractional values. So if you want some more points to plot, if you want to see, you can change your t. Instead of counting by ones, we can make it a decimal value by going back to second window to our table setup. And start at 0. And we could go by like 0.5 or 0.25 or 0.1, whatever you want to see it by, and see some more values. So we know that at half, when t is 0.5, there's going to be a point at 1.43. So we'd go over like 1.5-ish, 3. So there's a point here. Okay, and you can kind of get however many points you need. Okay, but the quadratic form in rectangular form is going to be more helpful for getting us points up here to guide our curve. So for instance, if I plugged in a 3, that would be 10, right? Because 3 squared is 9 plus 1 is 10. Okay, so that can help guide. Oh, didn't get that drawn very well. Guide that, and we don't put an arrow on the end like with a quadratic. Okay, so we're going to put arrows along this showing the direction as t increases, it's coming down this way, right? And you can label some of your t values. So we said that 1, 2, that was when t, already forgot, was 1. Okay. You get really close in, like when t is 4, you're at half 1 1/4, like right here. Okay, that's where t is 4, if you want to label that one. Okay, so you just label however many, a couple of t values, and you have the arrows drawn showing the direction. Does that make sense? Okay, and we can get the end of it. Where exactly is the end of it? Where should that be? Because we know that t is never going to be negative and it's not going to be 0, right? So like we could try and get real small. With right now, the smallest we have is 0.5. Let me change that. Let's go to like 0.01. So there's a point at 10, 101. So with our graph, it doesn't get cut off. There's still points up there. T is just minuscule values, right? So that you can show that going all the way to the end. We're not going to see the end of it. Does that make sense? All right. All right. I'm going to give you the practice. You're going to be doing the front side is algebraic practice without graphing. It's just eliminating the parameter and things like that. And then on the back, there's some graphing practice. Okay, so this practice will be due, what is today? Tuesday? Today's Wednesday. So I'll make that due on Friday. I think I wrote it on the board already. Okay, so that's going to be due on Friday.